So, welcome to the Mechanical Unit Operation course, the discussion for the week 7. Today we will discuss about the flow passed through the various fixed bed as well as fluidized bed kind of configuration. Why we need that? Because in the chemical engineering there are many applications where we need to understand the parameters and interaction between the fluid particle, a fluid flow as well as solid particle. Okay, so I want to share my screen. I think everyone can able to see my screen now. So I just want to start the presentation. Okay, so today is the today is the week 7, flow through packed and fluidized bed, and there are 4 different lectures in this week 7 close module. 2 are dealing with the flow through bed of solids, or you can say packed bed of solids if you want to go into more detail, and the other 2 are discussing about the flow through the fluidized beds. Okay, so this is the outline of our today's discussion. We start with why we require to flow through bed of solid particle. Then pressure drop calculation we will take care of, understand how pressure drop calculation is required, and there are many problems are there whom which you need to find the pressure drop when the fluid is flowing through the bed or fluidized bed and solid particles and interaction with the fluid. So then after Reynolds number and friction factor relation, then some general characteristics of gas solid and liquid solid systems. Then most important one topic is that minimum fluidization velocity of gas solid and liquid solid fluidization. Then after we will discussing some examples, and at the end disadvantage of fluidization. In this today's discussion I only cover the topics which were relevant to your assignment and some exam problems, and some exam problems kind of criteria as well as topics. I didn't go through the much detail in the theoretical aspect, but where and when is required I touch the theoretical aspect, try to understand it and try to recall you that what is there actually expect was, and how we will implement into the example solving, or else you can go through the professor's lecture if you want to go in much more detail. Okay, so let's start. So first is flow through bed of solids. The first lecture, the first questions which arrive in our mind is the flow through bed of solid particle. We just now discuss the solid particle or solid one solid particle, not solid particles, one solid particle interaction in the fluid filled in the some container, cylinder, anywhere. We just discuss about the drag forces, which kind of viscous forces and all which will be there, that will be responsible. But why we require the flow through bed of solid particles? There many solid particles are there. There is typically alternative of what we already discussed, and then we discuss about the fluid which will be flow through. Okay, so flow through beds of stationary granular solid is often found in chemical and processing industry. You can see whenever we discuss about the distillation operation or many other operations where we require the columns and packing materials are there to enhance the mass transfer and heat transfer area between the two phases. So at that time we require to understand what is the flow behavior, how the pressure drop and how the other parameter and force will be acting on it. That's why the pressure drop across the beds due to the resistance caused by the presence of particle is prerequisite. This is a prerequisite which needs to be understood when we are talking about flow through bed of solid particle. Then the resistance to the flow of fluid through the voids in a bed of solid is resultant of the total drag of all particles in the bed. We discuss about the drag force, but here you can see that flow of there also resistance is there to the flow of the fluid. through the voids in the bed of solid. There is a bed of solid, you can understand, there is a bed of solid is there, fluid is flow through it. Although in this way voids also drag forces will be there. So how can we consider the drag forces? We need to consider the total drag forces. So total drag forces of all the particles in this particular bed, we need to understand about it. As in the drag of single particle, there is no sharp transition between laminar and turbulent flow, like that occurring in a flow through pipes and channels of constant cross section. So yeah, for single particle we are not discussing about the single particle, so there is no sharp. You can consider that there should be laminar region, there will be high velocity is there, so turbulent region. You need to consider that it's occurring between the flow through pipes and channel of constant cross section, and then after on the basis of that data you need to calculate. And one more thing I just want to say, due to uploading the video of the YouTube, the recorded video is uploaded every time. So I found that the voice is not that much properly coming in the videos, YouTube videos. So in this particular video, I try to switch off my all the fans in the room, and I try to speak a little bit louder than usual. So maybe if you found any improvement in this particular lecture, please you can let me know, or I will check after the recording. And if you talk about the flow through bed of solid, sorry for the interruption. First is the common method of calculating the pressure drop through a bed of solids is based on the estimate the drag on solid boundaries of the tortuous channel through the bed. So obviously there will be many channels will be formed when we pack materials would be packed into the column. So this tortuous that will be you can say that it is not regular, irregular patterns of the channels. You need to consider them and find out the drag forces on all the solid boundaries on all these kind of channels. Now next, so as you can understand, is that in the packed bed we are not always following the spherical packing material also. So channels are always irregular in the shape. If we are using the spherical material, then also channels are irregular, and it has a variable cross sections and orientation, and there is, you always should know that they all are highly interconnected. So that's why the impact of one part of the channel or one part of the fluid and particle interaction will be transferred to the whole as such, whole packed bed as such. So however, but we need to understand one thing, that whenever we need to find the calculation of the equivalent channel diameter, we need to assume that the bed have a set of uniform circular channels. Although it is not a real, their channels are always irregular in shape, but when we are going to calculation for the equivalent channel diameter, we need to always consider that the channels are the uniform circular channel and whose total surface area and void fraction match those of the bed. So that's why we can, at the end, we can get one particular kind of mathematical form which we can use for finding the pressure drop across the bed. So here, for getting the total surface area, we need to consider that circular channels are uniform. So for total surface area is equal to number of particles into surface area per particle. Okay, so we will find the surface area per individual particle, and because of uniformity, we directly need to just multiply with the total number of particles. At the end, we will get the total surface area. Now, it is made convenient to base the calculation on the volume fraction of particle in the bed and the surface volume ratio for the particles. As we discussed in the first 1 or 2 lectures, that we need to consider when we consider the packed bed configuration, where we always majorly we consider the surface to volume ratio. So diameter on the base of surface to volume ratio, other thing is that Sphericity is another parameter which comes into the picture when we are consider this surface to volume ratio kind of calculation. So you always need to remember phi s is equal to 6 Vp divided by Sp dP. Surface to volume ratio is, you can consider, for the, if you talk about the sphere, then pi dp square is the surface and the volume is pi dp cube by 6. So then you will get 6 by dp. So 6 by dp of sp by vp, that is nothing but your sphericity. So for irregular particle, we need to convert them into the sphere. So that's why we will use the sphericity, which is nothing but 6 Vp by SPdP. The particle volume fraction in the bed is 1 minus epsilon. We need to consider volume fraction. Voids, we consider void fraction is epsilon. Then particle volume fraction, that means 1 minus epsilon, where epsilon is the porosity of void fraction. Okay, porosity of the void fraction. Remember this thing. So this is basic understanding why and how we are going for this lecture and why it is required. Okay, so our main focus is that we'll not discuss today to each and every step of the derivation of pressure drop calculation, but we will just revisit the major formula which is required to calculate the pressure drop. So for starting with the pressure drop, was first and foremost thing is equivalent channel diameter. Okay, so we consider that there is channels are there. So channels, different kind of channels are there, but here we will consider that all channels have equal dimension and size, and then the diameter of the all channels we will consider as a average diameter of the channel we will consider as a equivalent channel diameter. So the actual bed is, this is the approximation you need to understand. So actual bed is a bunch of n number of capillary tubes, as I mentioned here, packed together, and the flow is taking place through the capillaries. So all the flow is taking place in individual capillaries, and these all capillaries packed together to make one packed bed. This is the approximation we will consider for the derivation of the formula. Now, so this here I just denote the equation of the D equivalent diameter. So D equivalent is equal to 2 by 3 multiplied by epsilon divided by 1 minus epsilon, void fraction divided by 1 minus particle fraction, phi s sphericity into particle diameter dp. So for typical void fraction, if we just want any example for this, then you can consider that if your void fraction is 0.43, then you have to substitute the value of 0.43 here and 1 minus 0.43 over there. Okay, so you can consider that 57, 1 minus 0.57. So and then you calculate this mathematical part, then you will get 0.503 phi s into dp for typical void fraction of 0.43. Majorly the void fraction which in general calculation we will consider that between 0.4 to 0.45 or 0.46. We consider this kind of void fraction in our calculation, and that is generally commonly available in the real world situation. Other thing, so how we will transfer this data, this information in order to find the pressure drop. So we know that for the laminar flow, Hagen-Poiseuille equation is there. Hagen-Poiseuille equation will provide the value of delta P, that is nothing but the pressure drop between the laminar flow. So we consider in this that when we derive the Hagen-Poiseuille equation, we consider that in the cylindrical laminar flow, this is the equation 32 L V bar mu divided by P square. Okay, so we will use the same equation here for the laminar flow region, or we can assume that if there will be laminar flow, we will use the same equation, but instead of d square we will use the equivalent diameter square, that is the equivalent square. Okay, and then we will go for the calculation. Now as you can see that at the end, after substituting the value of the equivalent, so for the laminar flow, this is the equation which you got. Delta P divided by L is equal to 150 V naught bar mu 1 minus epsilon whole square divided by phi s square dp square epsilon cube. Okay, so this is the equation, and maybe if you want to go in each step of the derivation, then you can refer the books, and you can go through the professor lecture also. So this you have to remember this equation that is known as a Cosne-Kármán equation. Okay, and that we will use for the Reynolds number up to 1, but generally we can use up to Reynolds number of 5 to 10. So here you can see the difference. For cylindrical flow without solid, we will consider the Reynolds number, laminar for Reynolds number is up to less than 2100, but for here we consider Reynolds number up to 5 to 10 in the laminar region. Why? Because here solid particles are much more dense packing is there, so this laminar Reynolds number only provide the laminar flow. After then, if Reynolds number will increase to that, then it will convert into the transition and subsequently turbulent flow. So you need to keep remember that this is not the same, although if we are using the same kind of cylindrical arrangement, but this is a packed bed. Okay, so for the Cosne-Kármán equation you can use for the Reynolds number up to 1 or 5. So now making use of turbulent flow equation for flow in straight lines for the present case. So now we will use the turbulent flow equation which include the fanning friction factor or friction factor in general, for getting the equation for the same kind of equation for the pressure drop in the turbulent region. So this is the equation: delta P by L 2F rho V bar square upon D because we converted into the equivalent diameter, and lambda 2. Lambda 2 is the correction factor. Here also you consider there is a correction factor was there, and we will get the value of correction factor is 150 times. Same here we can also consider the correction factor, and this is the equation. So empirical equation which is available for the packed beds at REP greater than 10 to power 3 is Brucker-Plummer Burke-Plummer equation. Okay, so delta P by L, you can pronounce sometimes Brucker, also it is written in some textbook, but you can be Burke-Plummer equation, or which is equation for the turbulent flow. So here delta P by L is equal to 1.75 rho V square, because it comes from here, and there is d square, this whole ul mu by d square will come from the laminar flow Huygens-Poiseuille equation. So rho V naught square upon phi s dp into 1 minus epsilon divided by epsilon cube. It is little bit different than the epsilon cube is both the places, but 1 minus epsilon square is there in the terms of laminar flow, and here 1 minus epsilon only. Okay, so equation covering entire range of flow rates. Now we just consider that laminar flow region and turbulent flow region. If you want to consider the equation which can add the both laminar as well as turbulent region, and we can apply this equation in each terms. So which consists the viscous loss part, which is generally equal viscous loss part and kinetic energy loss. So on the summation of both the part, we can get the value of the total equation, which is nothing but known as a Ergun equation, which is very important equation in the flow through packed beds and flow through fluidized beds. So Ergun equation is delta P by L is equal to the summation of both the Cosne-Kármán equation and Burke-Plummer equation, 150 and 1 minus epsilon square upon phi s dp square epsilon cube plus 1.75 rho v square upon phi s dp 1 minus epsilon upon epsilon cube. So you always remember this equation, because it is very important in terms of the gate examination, sometimes in terms of the solving the assignment of this chapter, as well as with reference to the NSEM examination for this subject. Okay, so there are some characteristics of Ergun equation which I noted over here. Ergun showed that Ergun demonstrated that the above equation can be used for the spheres, cylinders, as well as crushed solid. Everywhere you can use a similar kind of equation which has over a wide range of different flow rates. A small change in epsilon, and then you need to consider the one more important thing, if you just change if you do the small change in the epsilon value, it has a very large effect on the delta p, which makes it too much difficult to predict delta p accurately and to reproduce experimental values after a bed is repacked. Okay, so you can design this the effect pack bed, pressure drop and all, and you can get the value and you can design the pack. But once it is again repacked, you can't able to match the value with the original one or the previous value of delta p. Why? Because small change in the packing, you can say small change in the void uh, density, it will affect a very large, it has a very large effect on the delta p. So that's why it is you need to consider that thing. Now there is one more one important part of this chapter is there is one Reynolds number and friction factor based relation for the packed beds. I just want to use that equation in my presentation for the revisiting or all or for just revising purpose or revisiting the professor's lecture purpose. So you just reminded it and you can use it if it is required. So the equation is like that: friction factor Fp is equal to delta P by L dP upon rho V O square epsilon Q upon 1 minus epsilon. So if you substitute the value of dP, the equivalent in this equation, at the end you will get that 150 divided by Reynolds number plus 1.75. So this equation will convert into the Reynolds equation after some derivation or some steps, and at the end you will get the value at 150 by Rp plus 1.75. So you can easily remember this equation, and you can get if someone asks about the Reynolds number, then you can directly find out what is the friction factor associated with it if we are talking about the packed bed, and someone asks vice versa is also possible. So as we mentioned before, if you just use the above equation, for the laminar flow your Reynolds number should be in between 5 to 10, while if you are talking about the turbulent flow, then your Reynolds number will be greater than 2000. Okay, here for the turbulent flow there will be no much difference is there, Reynolds number is much higher, but for the laminar flow the value of Reynolds number is too much low with respect to the flow. Okay, and the general characteristics of the gas, liquid and liquid solid system, it's another discussion. Why it is required? Because there are many theoretical based questions will be there, many fundamental understanding is required when you are deal with the different kind of fluidized bed systems, and you need to understand how velocity and pressure drop is related with the fluidized bed properly. Okay, so first, if you there might be two types of different flow you can consider in the fluidized bed or any packed bed. You can consider upward flow through bed some particles, and there will be a downward flow. Okay, in the upward flow through beds of particles, so just ignore the background noise. So upward flow through bed of particles. So if you just consider the upward flow, then upward flow, that's like you can consider that if here the packing is there, okay, so this is most important thing, because generally fluidization is only occur when we provide the upward flow of particles, because it is against the gravitational force. That's why if after buoyancy it will float into the air. So if we just constrain this bed on the top, then there will be no any difference. It will be same as a downward flow. So if bed is constrained at the top. Okay, another thing is flow is such that the structure of bed is not disturbed by flow, or it is same as a downward flow if our structure bed is not disturbed. That means velocity of air or any fluid material is too much slow. By gradually increasing the flow rate of particular fluid, the point at which drag on particle becomes equal to their buoyant weight, then you can consider that there will be fluidization occur. So there will be one point which drag on particles becomes equal to their buoyant weight. So drag on particle, which is equal to the buoyant weight. And after that, if you further increasing the flow rate, then bed gradually become loose and reaches a point where particles are separated from each other. Okay, so after that bed will be reached at the point, then particles start to separate from each other little bit, then they will float, and then there will be fluidization occur. So once particles start separated from each other, then particles become freely suspended in liquid stream, or you can consider it a fluid stream, and bed is said to be under fluidized conditions. So by further increasing the flow rate, particles move further apart, causing increase of bed voidage, but pressure drop remains. So you can say pressure drop remain approximately constant. So after fluidization system occurs, then you can consider that your bed has like this condition. So fluidization is occurring and some bed is still in the static condition. So if you again further increase and everything is in the fluidized mode, then you can consider that there will be no further pressure drop will be increased. Pressure drop will be almost constant, and you can consider, yeah, because there will be only whole flotation is there, so there will be constant pressure drop is applied throughout. So this is the pictorial representation what we just discussed. As you can say, this is a fixed bed, this is some length of bed is there. If we apply any kind of gas or liquid velocity, if velocity is very low, then it will remain into the fixed bed, there will be no any difference in that. But if we will increase the velocity further, then you can see there is little separation of the particle is happening, and that is known as a minimum fluidization. In some particles, some minimum fluidization velocity required to reach up to that flow rate of gas and liquid, and after that flow rate, the separation of the particle will start, and it is known as a minimum fluidization. Then if you just discuss about the liquid, then if you further increase the flow rate of liquid, then there will be there you can say equivalent distance. There will be every particle is situated at equivalent distance. There will be no much difference, and there will be uniform pattern of solid particles. That is known as a smooth fluidization. Okay, so but why it is happening? It is only happening in the presence of liquid, because liquid has the molecular configuration which is not much apart. They will just mix the solid particle in between them, and you can see the constantly uniform fluidization is occur. It is also known as a smooth fluidization. But if you talk about the gas and you increase the gas flow rate, then you can see there will be some places where gas molecules are very rigorous, or you can say just started to rigorous, and you can see the bubbling of gas molecules can happen. That is known as a bubbling fluidization. Okay, this is not a part of the liquid. You always use gas if you talk for the bubbling fluidization. Then you further increase the velocity, then you can see that small bubble is coagulated, or you can say agglomerated with each other, and they form the big bubble. So you can get sludges, and this sludges is favoring in the sludging. So you can say this even higher gas flow rate, the bubbling fluidization can be converted into the slugging fluidization, or you can get slugging. So here in the slugging also different configuration are there. If you further increase the flow rate, then there will be many void section available in between the packed bed. So they are known as the flat slugs. And you further increase the flow rate, then you can see there will a turbulent fluidization happen. You can't predict any kind of particular shape or size and a particular pressure drop available at each and every space is not same. They are all different, and you can see a different pattern, like it's a turbulent flow, and it's known as a turbulent fluidization. While this same kind of principle is used for the pneumatic transport of the solid particle, where we apply the gas and liquid is very high velocity to transport this solid particle from one place to another place. but for that we are not, you can consider that it is known as a lean phase fluidization with pneumatic transport, because our main purpose is to transport this solid particle from one place to another. So that is our another kind of application where we are using the fluidization. Now the same kind of pack bed configuration is represented with gas velocity. As at low gas velocity, fixed bed is there. Further, as if we increase the gas velocity little bit, then there will be bubbling fluidization. Further increment can be converted into the turbulent. So here we talk about only gas, and the solid we can, here in the turbulent fluidization, if we want, we can return some part of the solid to the back of the bed, and then if further increasing the gas velocity, that turbulent will convert it into the very fast fluidization, and at the end you will go for the pneumatic transport. And this is the textbook figure. Here we already discussed L by M, LM, sorry, L by M, I forgot, I by mistake speak L by M. LM is there, gas or liquid velocity, low velocity fixed bed will be there. By increasing the velocity, it will convert into the minimum fluidization. It has some separation of the particle, but not much. Then particulate fluidization is there. In that particulate fluidization, as you can consider that if you, it's uniform fluidization for liquid. If you use the liquid, then you will get subsequently this kind of fluidization, which is also known as a particular fluidization. Talk about the gas, then bubbling fluidization, slugging, axial sludges, and there is sludging or slugging where flat sludges are there, and turbulent fluidization, and at the end pneumatic fluidization, which we are using to transport the solid particles. Okay, now liquid solid fluidization. Okay, so here we need to understand. So this is the graph, log by log graph of log delta P, pressure difference, or you can say pressure drop versus velocity. So here you can see when you are increasing the velocity, the pressure drop is constantly increasing. After at the point A, after this point, this increment is not linear. You can see some curvature, because there is separation of the particle was started at point B, and after that in the proper fluidization is occur, and after that in the fluidization you will not see any difference into the pressure drop. That's why you can see the constant pressure drop line after that. But here this shape is occur due to separation of the solid particles. And if you want to just reducing the gas velocity, then as you can see, after it will remain constant up to the point E. Okay, which is corresponding to the point A, you can see, and this E point is known as a fluidization point. Up to point E you will get the fluidization, you can see the fluidization in your pack bed, but before that in here this period, after that this period you can't see that kind of fluidization. So you can consider this velocity as a fluidization velocity or minimum fluidization velocity, or bed of maximum porosity. And then if you reduce in the velocity, and you will get the pressure drop difference, but that is different than the earlier one. Why? Because you can pack bed very accurately in the first time, but when back will pack and the bed is all packed by itself, then it is always different than the initial original packing. Okay, that's why you need to always remember all these things. Now if you just talk about the bed height versus superficial velocity is the minimum value. Superficial velocity is the velocity we talk about, that where we don't have any solid particle in this, and we just flow our fluid. We increase the velocity, and at the end it will reach up to the fluidization velocity. The bed height will be constant. After that, when it reach up to the fluidization velocity, you will see this same increment on the bed height as constant pressure drop will reach. And that's why the pressure drop versus velocity, it can be separated two different bed, that is a fixed bed versus fluidized bed. So if you, for the some amount minimum velocity required, you just bed is only fixed bed. After that, attaining that velocity, your bed will convert into the fluidized bed, and this data is experimental as well as modeling experimental data which we draw here. Okay, so after this minimum velocity only, it will convert into the fluidized. Now minimum fluidized velocity, as we discussed, minimum velocity required to start fluidization, velocity of gas, liquid, gas solid and liquid solid fluidization. Okay, so how we will go through. So here we will not go for all the derivation. After that we will see many examples on it, and we will see that how these examples are working. So for finding the minimum fluidization velocity, pressure drop across the bed we need to consider is equal to gravitational force minus B1 force divided by unit cross sectional area. Okay, so fluidization is already occurring. That's why you can consider that for the minimum occurring, we need to take the difference between both the forces at particular cross sectional area. So you will get this for equation, which is delta P by L is equal to 1 minus epsilon G rho P minus rho. So that is much more important, and it many times GATE exam has questions on the basis of this particular equation, and in this course you will get the assignment question and final exam question on the basis of this equation. So at the minimum fluidization condition, we will consider the voidage is also minimum, epsilon is equal to epsilon m, and the velocity is obviously minimum. V naught bar is equal to V naught bar m. Okay, so we are using the same Argand equation where we just convert our V bar into V1 bar, V bar OM, and VO bar V naught bar, or V naught bar into V naught bar m, V naught m bar, and epsilon equal to epsilon m. Okay, so there is, you need to understand, this may be the assignment question, so you need to understand there are some discrepancies between the observed and calculated minimum fluidized velocity. Why there are there? So observe, you find some calculation for the velocities, but they need to not be the same as the observed or experimental velocity. Why it is that? So there might be channeling is there. You can't consider each and every channel because you consider channel is uniforms. There might be wall effects are there. There might be agglomeration of small particles and interlocking of particles. It's always there when we talk about the solid particles. So this kind of discrepancy you need to consider. So that's why your theoretical value does not necessarily match with your practical experimental value. Please ignore the background noise. Now for spherical particle, there is one equation in that Ga is equal to 150 Reynolds number m rem plus 1.75 Reynolds number m square. So here Ga is a Galileo number. Okay, this is also one dimensionless number which we are using directly in the, if you want to find the Reynolds number, velocity, or many important thing in this calculation. And the Galileo number has the that number is directly count the simplification of the above equation. There is no new in that. So Galileo number is equal to G rho P minus rho dP cube by mu square epsilon of m whole cube 1 minus epsilon m square. Now Reynolds number at minimum fluidization is Rem is equal to rho V naught m bar dP upon mu 1 minus epsilon m. Okay. So there may be question is there. You need to first find the Reynolds number many of the times, and there are directly question in which they ask for the Reynolds number for the minimum fluidization. So you need to understand how to calculate those. Now we start with our examples. Okay. So first is consider a packed bed. Consider a bed packed with spheres of diameter 1.871 meter. Okay. So our packed bed has a sphere, small spheres, which has diameter of 1.871 millimeter and whose voidage epsilon is 0.46. Then what is the corresponding equivalent channel diameter in millimeter? So we need to find the equivalent. For the D equivalent, there is a just you need to put the values in your equation. That's it. In this, it's a very easy and simple example. As you know that D equivalent equation is there, we just go through. D equivalent is equal to 2 by 3 multiply by epsilon upon 1 minus epsilon phi s, yes, but that is sphericity. And if we talk about the sphere, then sphericity is equal to 1. So when we talk about the sphere, because 5s is equal to 1, sphericity denote that your particle is how much near to the sphere. But if you talk about the sphere itself, then it is always needs to be 1. Okay, and the diameter, particle diameter, that's it. You just need to substitute your value, and at the end you will get the equivalent channel diameter or equivalent diameter, which is nothing but 1.594 millimeter. Okay, so this kind of equation and this kind of problem you might consider for your assignment. Maybe there you can check it, and maybe you consider for your different examination. So this is very simple parameter example, but you just need to remember the equation, or you can derive the equation, that's it. But if you don't want to waste the time, you can remember also. Now there is another example in which consider a bed packed with spheres of diameter 1.1 millimeter. Here the dp is equal to 1.1 millimeter, whose voidage is 0.46. I just considered the same void. What is the average velocity of the fluid flowing through this bed in meter per second if its empty tower velocity is 0.867 meter per second? And superficial velocity or empty tower velocity is 0.867 meter per second. It is given. Now you need to consider, you need to find that average velocity when this diameter particle will be packed into the packed bed. Okay, so it's easy, and you also get the value of epsilon, it's already there. So how will you get the average velocity, which is a superficial velocity or the empty tower velocity divided by the epsilon or voidage? So your superficial is 0.667 divided by 0.46, then you will get the average velocity of the fluid flowing through the fluid through the bed. So V bar is equal to 0.867 divided by 0.46. That is nothing but 1.885 millimeter per second. So you always need to remember one thing, that empty tower velocity is always less than the actual average velocity. Okay, obviously, because there will be no empty tower, we can't say every time, but yeah, generally that will be mostly less. That because empty tower velocity is only interact with the own particles, but if we have the packed bed, then there will be channelizing are there will be low pressure, so low pressure is always converted into the high velocity. Okay, according to the Bernoulli's equation. So pressure will be low, pressure will be high. So according to that, your velocity will be defined, or you will get a value. Now consider a column of diameter of 0.82 meter. Diameter is 0.82. This is a not particle diameter. Or height is 3.59 meter. Spheres of diameter is 13.89 millimeter have been used to fill the column in order to make a packed bed. For packed bed, this is the sphere which they use. A fluid of density 1.221 kg per meter cube and viscosity 2.23 into 10 to power minus 5 pascal into second is flowing through the packed bed at the mass flow rate of 0.296 kg per second. What is the value of Reynolds number? Take the voidage is 0.39. So as we discussed, many of the times they will directly ask you to calculate the Reynolds number for particular conditions. So here for here you first start with the cross sectional area of the bed. Okay, why? Because for finding the Reynolds number you require the cross sectional area of the bed, so which is nothing but the pi d square by 4. So here column diameter is 0.82, so you multiply 0.82 into pi by 4, and then you will get 0.528 meter square. And here you have the value of d particle diameter is 13.89 millimeter. You need to consider into the meter as we follow the SI unit. So 0.0139 meter, and length or height is given as a 3.59 meter. Okay, so Reynolds number equation is like that, rho v0 bar dp upon 1 minus epsilon mu. But This is here V0 bar is always we don't know most of the times. So that's why rho into V0 bar we consider as a G. G is a mass velocity. Okay, so as you can consider meter per second into kilogram per meter cube, it will be converted as kilogram second into meter square. So it is nothing but the mass velocity you can consider. So here we need to calculate the G. G is nothing but rho V naught. But how we can there is one equation. If you want to find the rho V naught bar is equal to G is equal to mass flow rate divided by the cross sectional area. You will get the same kind of equation. So same unit as mass per kilogram second into area. So same. Okay, so for that we have the mass flow rate 0.296 and the cross sectional area we just find it. Okay, that's why we require the cross sectional area in our Reynolds number. So cross sectional area is 0.528 and we'll get the 0.561 kilogram per meter square into second. We just substitute the value in Reynolds number equation and then we'll get the Reynolds number is 548.64. So a bed is made by filling a column. There are many examples included in today's lecture. You can get a better idea by solving them or just understanding them. So here you can see that bed is made by filling. So peg bed is made with the help of filling of 8.33 centimeter diameter particle with the total bed diameter is 8.33 centimeter by using the spherical particle, where spherical particle has diameter of 0.98 millimeter and density of 1380 kilogram per meter cube. So the bed is fluidized with a solution of density and viscosity. So there is one solution which is used to fluidize the bed, which has a density of 970 kilogram per meter cube and viscosity of 0.0088 poise. What is the voidage at 32% expanded bed condition if the voidage at minimum fluidization condition is 0.36? So epsilon m is given 0.36. We need to find as epsilon e at expanded condition. So here many information are given, but you need to find that all information is relevant to you. It is required all the information to use in the calculation or not. So we can it's not required. If you go to the theory, then you can find that there will be directly relation between the length or height versus height and voidage, or you can say the void section, void porosity. So LE by LM is equal to reciprocal of 1 minus epsilon m divided by 1 minus epsilon e. So this is a direct equation you can use. You don't need to bother about what are the parameters or the fluid particles, what are the parameters of fluid viscosity and all that are required. You just focus how much bed is expanded, 32%. So what is the difference between the voidage? That is to find. So at 32% expanded bed, L is equal to 1.32 Lm. You just take the value and you can find that at expanded bed you will get 0.5 voidage, which is 0.36 at the minimum, but at the expanded 0.5. Obviously voidage will be increased at expansion. You can consider like this and like this. Okay, a column of diameter of 0.79 meter and the height of 3.13 meter is packed with glass spheres. Okay, here it is mentioned that it is packed with the glass spheres which has diameter 11.47 millimeter and particle density 1524 kilogram per meter cube. Again we are flowing the fluid for the fluidization, which has a density 1.144 kilogram per meter cube, viscosity 2.22 into 10 to the power minus 5 Pascal into second, flows through the bed at a mass flow rate of 0.478 kilogram per second. That is sufficient to incur minimum fluidization condition in the bed. This condition is sufficient to incur the minimum fluidization. Then what is the pressure drop at the minimum fluidization condition if the corresponding voidage is 0.265? Okay, so here that is the equation is very simple. Delta P by L at minimum fluidization, we need to find the delta P. L we have 0.79 is diameter, L is 3.13, 1 minus epsilon 0.265, G is 9.81, rho P we have and 1524 and rho we have. We just substitute a value, we will get a value of delta P by L is equal to 1090.325. We just substitute, we just take the L to the other side, put the value of L 3.13, and then you will get 34.368 kilopascal. So at the when we just talk about a minimum fluidization condition, you without thinking much you can use this equation. Always remember that thing. Okay. Now a bed consists of uniform spherical particles of diameter 3 mm and density 4200 kg per meter cube. What will be the minimum fluidizing velocity in a liquid of viscosity 3 millinewton second per meter square and density 1100 kg per meter cube? Assume voidage at minimum fluidized condition is 0.4. So epsilon m is already given 0.4. All other values are also given. Now we need to find that what will be the minimum fluidizing velocity. VOM bar. So this is very important questions in order to design the bed, and this is little bit complicated than earlier. So we visited earlier examples. So here you need to consider what is a diameter particle. Everything needs to be considered in your calculation. So diameter particle is 3 mm, the density of particle epsilon m. Sorry. And you can consider the equation of this. We will go through the equation of Galileo number first. That is easy. Galileo number is some factor of Reynolds number, or it is a simplification of the complex equation. So you need to find the Galileo number, which is g rho dp cube rho p minus rho upon mu square epsilon whole cube 1 minus epsilon m square. Galileo number, you have to substitute the value of each and every value you have. You substitute, you will get one value, that is a Galileo number 17841.12. Now, so that is the equation. Galileo number is equal to 150 Reynolds number at minimum fluidization velocity plus 175 Reynolds number whole square minimum fluidization velocity. You just put the value and you find for the, you solve the equation, quadratic equation for the Reynolds number at minimum fluidization velocity. You will get the value. Reynolds number is equal to 66.8319. Okay. Now after at minimum fluidization velocity, if you want to find the minimum fluidization velocity, you have the Reynolds number, you have dp rho mu 1 minus epsilon, then you can able to find a VOM bar. So after substituting the value, and then you will get minimum fluidization velocity 36.44 millimeter per second. I'm not go through how to solve this equation. This is how to get the roots, so you can easily take it. Okay, you can understand all these things. Now there is one example in which packed bed of small cylindrical particles are there, which has diameter of 0.0127 meter. Void epsilon value is 0.4. Height of the bed L is equal to 3.66 meter. Air enters at this particular temperature and this pressure 2.2 atmosphere air, where viscosity and density of air is given. Air flow rate is also given. This is solved example by professor. I just want to go to that equation, that examples, because you can also consider the different flavor of the example. You can get to know different flavors of the example. Here mass velocity is given, delta p is need to find. Okay, so sphere volume equivalent diameter can be taken as dp. So how to find it? Here you get this equation from 5s is equal to 6 vp upon sp dp. So for dp 5s is equal, dp is equal to, sorry, anyway it's fine. So dp is equal to, you have to substitute the value of 6 by 8.7. You have to find the volume as well as surface parameter. So sphere, you can say that this cylinder, so 2 times pi d square by 4 and pi d into L is equal to d, so pi d square, and then you will get the value of dp. After just solving this equation, you can directly understand. 1d here, that is 2d is went, 1d is there, pi d 4 has went, but then d by 0.847, you will get the value of diameter is, particle diameter is 0.0815 meter. Now you can find the Reynolds number g dp 1 mass epsilon mu. So you already have the value of G, so you can consider, and you will get the Reynolds number 3224. After that, so the same equation, which is Argon equation, you will use delta P by L, and this is the equation. In terms of mass velocity, you can convert that equation into the rho V0. So you have to multiply by rho. Here rho V0 by already square. So you multiply by rho, and in the denominator also you will get rho density, and you have to substitute and simplify the value. You will get delta P is about 23.963 kilopascal. Okay, there is one more example. In the column of diameter 0.75 meter and height of 4.23 meter is packed with spheres of diameter 11.6 millimeter and particle density 1750 kilogram per meter cube. A fluid which is air, which has density 1.3 kilogram per meter cube and viscosity 1.9 into 10 to the power minus 5 pascal into second, flows to a bed at a mass flow rate of 0.419 kilogram per second, and it incurred minimum fluidization in the bed. Calculate the voidage of the minimum fluid condition. So you first find, as we already discussed a similar kind of example before, so you find the cross sectional area pi d square by 4, and from that you another thing you need to find is that is a mass velocity 0.950 kilogram per meter square second. At minimum fluidization we have equation G rho P minus rho, and the other side is Argon equation. So you have to just substitute the value of rho, so you can convert it into the form of G, and you substitute the value, and at the end by simplification of that substitute all the value. By simplification of the equation, this equation, you will get the value of epsilon m. Okay, so it is not very complex. You have rho v m G is there, 1 minus epsilon m. Phi s dp is phi s is 1 because it is sphere. Here it is also not considered, so just you need to substitute all the value. That's it, and then you will find the cubic equation in terms of epsilon m that you need to solve. So at the end you will get the value of epsilon m 0.190. Then this is the, I think this is, they ask that you calculate the voidage at the bed at the minimum fluidization condition. So that's why you need to just find the value of epsilon m. Okay, yeah, that's it. Now disadvantage of fluidization. This is also very important topic, so I just want to touch to this topic, and what are the different disadvantages when you are using the fluidization. So one is uneven contacting of gas and solid. Obviously there is no even particularly uniform contact is available. It generally gas passes through the bed as bubbles and directly contacts only a small amount of solid in a thin cell known as a bubble cloud around the bubble. Okay, so there is bubble and there is a bubble cloud is there. So solid is this always like this kind of things are occur in the fluidization. Small fraction of the gas passes through the dense phase which contains nearly all the solid. So sometimes small fraction of gas passes through a very dense phase is there, and very small phase of gas will be go. This kind of disadvantage and situation can be occurred when we are using the fluidization. That I need to tell you. Interchange of gas between bubbles and dense phase by diffusion and or by turbulent processes such as bubble splitting and coalescence occurs. So that kind of thing is always occur because you are applying the velocity much higher, then there may be chance for the turbulent processes, and there will be bubble can be split, bubble can be coalesced, then many kind of things will be happen. That will be not advantage or process. However, overall conversion of gaseous reactant is generally much less than with uniform contacting and the same temperature as an ideal plug flow reactor. If you just talk about the ideal plug flow reactor, then sometimes conversion will of gas material. If you talk about the fluidized bed reactor, then it will be not sufficient or uniform. Average bed density in turbulent fluidization is lower than the bubbling fluidization. Obviously, density will be too much lower in turbulent fluidization. However, there exists better mass transfer between gas and solid in turbulent fluidization, obviously, which may improve the performance of the unit as a chemical reactor. When we talk about the chemical reactor, then you need to maintain the turbulent fluidization, which can be good for a better mass transfer. Scale up of the fluidized reactor is uncertain. You can't consider that whatever you got into the lab scale result, it should be the match with your final reactor. Erosion of vessel internal parts, attrition of solid leading to the loss of fines many a times is there. So these are some books and references which professor follow, and I also follow the same kind of books. Most of the topic covered from the unit operation of chemical engineering by McCabe and Smith, and some of from the unit operation of particulate solids. So at the end, as always, I today also I attached one quote from the Indian businessman rather than scientist this time, from the Dhirubhai Ambani, that he has a one famous quote which mentioned that for those who dare to dream, there is a whole world to win. So with that, please all the best to all of you in your assignments, submission, and final exam also, because it is very near in the next month only. So please be prepared. If you have any doubt, you can contact me on this mail ID. And yeah, happy learning. Okay, so I just want to stop sharing now. So thank you everyone to listening this talk, and I hope you have you are good learning so far. If you have any questions, just let me know. Thank you so much. Have a good night.